Hello everyone, in this video I would like to talk about my recent work on simulation of axions in the post-inflationary scenario. This has been done in collaboration with Kieran O'Hare, Javier Redondo and Yvonne Wong. My name is Giovanni and I'm a PhD student at UNSW Sydney. So I would like to start with the motivation, and my starting point is the CP violation puzzle in the strong interactions. This has been known as the strong CP problem and is essentially a conflict between theory and observations. So on the one hand, the theory predicts a CP violation source which is proportional to an angular parameter, which should be in principle proportional to an order one parameter. While on the other side, we try to measure such a CP violation source through the neutron electric dipole moment. However, its non-observation leads to a very strong constraint on this angular parameter. So this very small number really calls for a dynamical explanation, which was the idea that was proposed by Peccei and Quinn 45 years ago. And the main idea is, what if we extend this angular parameter to a dynamical field and we let it relax to the bottom of its potential? And if the minimum of this potential is CP conserving, which is the case in QCD, then the problem disappears. And this dynamical field is now known as the axion field. And the Peccei-Quinn mechanism is simply adding an abelian global symmetry, which is spontaneously broken at a large energy scale called the axion decay constant, but is also explicitly broken at the QCD confinement scale, where the axion develops a potential and a mass. And interestingly, the oscillation around the minimum of the potential leads the axion to be a non-relativistic condensate, and it makes it an excellent dark matter candidate. So it is important in this timeline to understand when inflation takes place, because cosmologically it's very crucial to understand if it happens before or after the symmetry breaking. If the symmetry breaking happens before the end of inflation, then our present universe is made of one single initial value of the axion field, and there's really no way to determine the radical abundance of axions. It will depend on this random value. While if the symmetry break is after the end of inflation, then our universe is made of many regions that were causally connected patches at the time of symmetry breaking. And therefore, in principle, we could determine the relic abundance of axions just by averaging over these multiple values. However, the axion field in this case is very inhomogeneous, and the presence of multiple causal patches can lead to the formation of cosmic strains between them. Therefore, this scenario is filled with topological defects, also because at the time of QCD confinement scale, domain walls can form as the axion mass turns on. And on top of that, miniclusters can form and matter radiation equality due to order one fluctuation in the energy density. And so given the complexity of this scenario, we can only rely on numerical simulation to make predictions. And just in the last 10 years, there has been a huge advancement in the field, and we improved our understanding in this physical scenario. However, many open questions still need to be addressed. And in here, we want to focus on the following questions. So given the fact that axions start to become dark matter when the mass becomes comparable to the Hubble parameter, how is the system affected by the mass parameterization? Because for the QCD axion case, the mass or time dependence of the mass is given by the topological susceptibility, and is usually defined as a power law with a large index between 6.5 and 8. But in here, we want to keep the same mass parameterization, but we want to keep the mass index as a free parameter. And so we want to solve the Clyde-Gonod equation on an expanding universe for a complex scalar field where the axion will be the angular degree of freedom. And indeed, we performed a set of simulations with large resolution with this power law index between 0 and 6. And we evolved the system around the characteristic time, which is this time T1, which is defined as the time when the mass and the Hubble parameter are the same. And we evolved with the following assumptions. So first of all, we employed the so-called PRS trick. So we kept the string core to be constant in moving coordinates. So in our box, the string width is always the same. However, on the other hand, we cannot achieve physical values of the string extension because between the time the strings form at the scale FA to the time they get destroyed at the QCD confinement scale, there's a very large separation of scales that cannot be resolved by computer simulation or by computational resources nowadays. And therefore, our results are affected by this. And this is something that I will discuss also later regarding dark matter. And finally, we want to make sure that domain walls are unstable. So we set the domain wall number to be 1. And so I want to show, first of all, what does the evolution looks like on a snapshot. So you're looking here at the projection of the energy density. So at very early times, the system looks like filled by strings, which are in the scaling regime and are constantly decay into relativistic axions, which because are massless. However, as we approach the characteristic time, the mass turns on, and now we have a network of walls and strings. However, at some point, the walls will start dominating the energy density and start to pulling the strings apart and eventually collapsing the whole system after a few characteristic times. And so we are left with a bulk of non-relativistic axions, which are produced during the field oscillations, but also mildly relativistic axions, which are still free streaming in the box. However, our final simulation time, most of the grid is non-relativistic, and therefore we can apply an adiabatic approximation because most of the field values which will be smaller than 1, and we can linearize the equation and make an analytical approximation, which can be taken until matter radiation equality, where gravity cannot be neglected and the first overdensity will collapse into miniclusters. We want to study what is the mass parameterization impact on physical quantities that we can estimate in the box. First of all, we look at topological defects, and we can actually count the number of strings per Hubble volume, which are defined in this parameter xi. And we can see that at early times, the strings are in the so-called scaling regime, although there is a logarithmic growth due to the string tension. And after a few characteristic times, the walls start to destroy the network. And this is matching our analytical expectation because we define a time scale tau2 where the energy density in strings and walls becomes comparable. And after that time, the walls will start to literally pulling the strings apart. So the life of the strings is determined by this lifetime. At twice this time scale, we expect the network to be entirely destroyed. And when that happens, there's no reason for us to continue evolving the equation with the full complex scalar field, where we only keep the angular part and integrate out the radial mode. In that case, it's much easier for us to study the density contrast in the axion field. And in the bottom right plot, I'm showing the distribution of the density contrast at final simulation time for different values of n. And as you can see, as we increase the index n, much larger values of delta are allowed, but also much smaller values. So there's more of a contrast between the voids and the large overdensities. And the other tool that we use to study the substructure is the power spectrum. So in here, you're looking at the dimensionless power spectrum, which is just the dimensional 2-point correlation function. And as I said, this is the power spectrum that we have after we applied this adiabatic approximation. And as you can see, for all n cases, the peak of the spectrum lies at scales much larger than L1. And this modifies the naive assumptions that the overdensities are forming at scales of order L1. But also there's a very non-trivial shape as we increase from n equals 0 to n equals 6. And in particular, you can see that there's a central peak, which as we increase n, gets at larger and larger values, and also shifts at larger values of k. This can also be seen by looking at the projection at final simulation time. So I was showing n equals 0 before, and if you look at n equals 4 and n equals 6, it looks visibly different. As you can see, there's much more small scale power on much smaller scales as we increase n. So really the takeaway message here is that the structure appears at much smaller scale than L1 for all n cases, but the power spectrum of Hubble at n equals 0 looks much different than what the QCD axion case looks like at n equals 6 or larger. And also with the final density grid, we can also make some estimation on the mini clusters, because the largest order densities are literally seeds of what would be the miniclusters around matter radiation equality, and the typical masses can be estimated as the mass that can be enclosed on a volume L1 cube, and is typically 10 to the minus 12 solar masses. Although this will depend on the axion mass, but as we have seen in the slide before, the early miniclusters that will form will have a much smaller mass because they form on smaller scale. And we actually estimated the Halo mass function by implementing a modified per sector prescription, and we did that by smoothing the field on several scales and determining if a minicluster would form or not if the density field of in the smooth configuration was larger than a certain threshold, which had to be extended to include a collapse during radiation domination. So in the bottom right plot, you can see the Halo mass function, so the number of miniclusters per logarithmic mass interval, and I made a comparison between n equals 0 and the QCD axion and at n equals 6.7 at different times. Although this is assuming linear gravity, and a full nonlinear numerical study needs to be done in order to study properly the miniclusters. And finally, I wanted to discuss the dark matter production. So in the standard calculation, most of the axions are produced during the field oscillations, but in here we want to go beyond and take into account the strings in the walls. And so we actually counted the number of axions at the end of the simulations. And in here, I'm showing the number density of axion as a function of n. And as you can see, there's a clear distinction between the different values of n. In particular, you can see that n equals 0, the efficiency, the production efficiency is much larger because the strings on the walls contribution weigh much more than at n equals 6. But it's also interesting that for most of the cases, the production is actually less than what it would be by doing the standard analytical calculation. Although I want to stress again that these results are assuming a small string tension, which is what we could achieve with in our simulation. And this, if we would extrapolate to physical values, this could lead to substantially different results. Although this can be done as a comparison to the Claire-Moore simulation that have added string tension, which was manually adding a string tension to that simulation. And we can see that n equals 6, or for the QCD axion, the efficiency seems comparable. So the effect of adding string tension might not spoil our results too much. This seems not to be the case at n equal 2, where in the added string tension, the efficiency is much larger than what we have found. So this could be even larger than n equals 0, and this is something that we have to keep in mind. So the takeaway message here is that the axion production really has a variation with the index n. We've seen that ALPS are more efficiently produced in QCD axion due to the presence of strings and walls, but this would likely change as we add the string tension. This brings me to the conclusions, which is we have performed high resolution simulation for a class of axion-like particle models, and we focus on the mass parameterization. We have seen that simulating ALPS and QCD axions leads to very different results between the dark matter production or the substructure. So we have seen that QCD axion have much more small scale power in the power spectrum, and this will lead to a much more massive mini clusters. On the other hand, axion-like particles are much more efficient in the production, and the trend that we've seen as a function of n should qualitatively hold even at large physical values of the string tension. So thank you very much for watching this, and I will see you at the live discussion.